Welcome back, ladies and gentlemen, to another episode of Dave Does Math from Home. I promised recently that we were done with derivatives. We were moving on from Chapter 4. We were going to do some Chapter 5 stuff. I lied. We're back in Chapter 4. We're back doing some derivative stuff. Just for a bit, though. We're only passing through. We'll be in and out. Today we need to talk about Section 4.9, which is about antiderivatives. So we've spent a lot of time learning how to do derivatives. You start with a function, and based on that function, you find its derivative. We have tons of techniques to help us do this. We know how to do it with tons of different kinds of functions. It's pretty well established. So today is when we do that backwards. Instead of starting with a function and finding its derivative, we're going to start with the derivative of something and figure out what the function was that created that derivative. So we'll see some stuff that looks like this. F prime of x equals, let's say, 6x squared minus 14x plus 4. This is a derivative of some function that I don't know. But we can probably figure out what the function was, where all of this business came from. So if the derivative of this piece is 6x squared, the x squared piece we know came from an x cubed, because that's what the power rule does. The power rule always shrinks the exponent by 1 when you take the derivative of things that have constant exponents. And it also, to go from here to here, we would have shrunk this number by 1 and multiplied the front by the 3. So the 6 probably came from a 2 coefficient getting multiplied by this 3. This is the term that makes this for a derivative. This probably came from an x squared term. That's how it went from x squared to an x. Again, there would be a multiplying by 2 situation involved if we take this derivative. So this coefficient probably started as a negative 7. The 4 as a constant could only have come from a 4x. And now we're done, yeah? This is the function whose derivative is this. Except there's a tiny bit of a problem. This is also a function whose derivative is this. So is this. This original function that we started with could have had literally any number here added on the back end as a constant. And when we took the derivative to get this, that constant would disappear. Doesn't matter what it is. Whatever constant used to be here, that information is lost when we take a derivative. So if the only information you have is the derivative, then we have no information about what constants may or may not have been involved. So we have a plan. The plan is we're going to add an arbitrary constant c. C is an arbitrary constant. Because this original function could have had literally anything here. C is sort of our stand-in for anything you want it to be. It's kind of a variable in that it could take on any number of different values, but we tend not to refer to it as a variable because x is the independent variable. It's what's actually varying across the x-axis here, and we have y as the dependent variable that will determine your heights. So our variables are already spoken for here. C is, it's a constant. It's just, it doesn't change based on x or y. It's just a constant that we don't know. So we call it an arbitrary constant. It's c. And the derivative of c is 0. that's how we're going to do these. We're going to do a couple more simple versions, and then we're going to talk about notation. If we have a derivative that looks like, let's say the derivative is the square root of x plus the sine of x. And I want to know what the original function was. The square root of x here, that's the same as x to the 1/2. So if the derivative of something is x to the 1/2, that means that the original function must have been x to the 3/2. If you start with 3/2 and you subtract 1, that'll give you this 1/2. That'll be the square root. But we also need a coefficient here. The coefficient we get in the derivative is 1. Which means that whatever this coefficient started as, when we multiplied it by 3/2 in the derivative, it became 1. So the number that we can multiply by 3/2 to get 1 is 2/3. And we can always, the nice thing about doing antiderivatives is you can always check to see if what you're doing makes sense. Take the derivative of this. The derivative of x to the 3/2 is x to the 1/2 times 3/2. 2/3 times 3/2 is 1. That looks like it'll check out in the derivative. Sine is where things start to get pretty confusing for a lot of students, because if you're doing sines and cosines, the derivatives sort of cycle through each other in this pattern. And we get really used to this pattern having an order to it. And now when I say take an antiderivative, that order is sort of reversed. And so a lot of students will make mistakes. When they should be doing an antiderivative, they'll do a derivative, and when they should be doing a derivative, they'll do an antiderivative. So pay very close attention to the direction that you're going in, and basically just the direction. If we were doing a derivative of sine, the derivative of sine would just be cosine. Because we're doing the antiderivative is going to be negative cosine. And that's it. That's the antiderivative. Except that it's not quite finished. Every single time we take an antiderivative, every single time, without any exception, we're not finished until we add a plus c on the back end. It's very important. Don't forget about the plus c's. I absolutely will not hesitate at all to take off points on tests and quizzes for forgotten plus c's. Don't forget the plus c's. They're important. When we start doing differential equations, the plus c's will become extremely important. So don't sleep on those. Let's do some more examples. Let's do f prime of x equals 1 over x to the 6th plus e. We'll start with an e to the x. Let's also do an e to the 3x here. That'll be fun. Okay. 1 over x to the 6th is the same as x to the negative 6th, which means that if we want to find the original function that has this as its derivative, we need to find the function that you subtract 1 from the exponent and it becomes negative 6. So that'll be an x to the negative 5th. But again, we need a coefficient here, and whatever the coefficient here is has to be something we can multiply by -5 to get 1. So I think the coefficient here needs to be -1/5. I think that works out, because then the -5, when you take a derivative of this, the -5 times the -1/5 will give you +1. You subtract 1 from -5, you get -6. Yeah, that looks like it's good. E to the x should be extremely nice. We all know the derivative of e to the x is e to the x. So if you're doing a derivative, it doesn't change. If you're doing an antiderivative, it doesn't change, except for that plus c at the end. You still need the plus c. I don't want you thinking that the antiderivative of e to the x is just e to the x finished. It's not. The antiderivative of e to the x is e to the x plus c. We only need one plus c for this entire string of things because it's all one function, but don't forget about that. E to the 3x is more interesting. We still have this e relationship, so when we take a derivative, if we were doing a derivative of e to the x, we would get e to the 3x, and then because of the chain rule, we would have to multiply by the derivative of the inside, which is 3. So the derivative of this is e to the 3x times 3. The antiderivative of e to the 3x of 1 e to the 3x has to also include that e to the 3x piece. There needs to be an e to the 3x so that when we take a derivative we get e to the 3x. But when we take that derivative we're going to multiply by 3. So we need to find a coefficient that can multiply by 3 to get 1. And that coefficient needs to be 1/3. So there's an interesting sort of symmetry here. If you take a derivative of e to the 3x, you get e to the 3x times 3. If you take an antiderivative of e to the 3x, you get e to the 3x over 3. So that works about like you'd expect it to, hopefully. Hopefully you were expecting that. Time for a sort of general rule. Let's say the derivative of something is x to the n. I want the antiderivative of x to the n. In order for me to take a derivative and get x to the n, I have to start with an x to the n plus 1. And I need to choose a coefficient that I can multiply by n plus 1 to get 1. And that coefficient should be 1 over n plus 1. So the antiderivative of x to the n is, it's exactly like the product rule but backwards. In the product rule, we multiply by the power and then subtract 1 from it, right? When we're doing derivatives, we multiply by the power and then we subtract 1. When we're doing antiderivatives, we add 1 and then divide by that new number. So we're switching the operations. Instead of multiplying and subtracting, we are adding and dividing. So it's the opposite operations, and it's in the opposite order. In a derivative, you multiply first and then you subtract. In an antiderivative, you add first and then you divide. So it's like a perfect inverse. There's one more example that I need to talk about. Oh no! I hecked up. Okay, hold on. X to the n. The derivative is x to the n. The antiderivative is x to the n plus 1, 1 over n plus 1, plus c. I can't believe I forgot my own plus c. I was just talking about how important it is to not forget the plus c's. This is foolish. I apologize. Okay, the one more example we need to do is f of x equals 1 over x. I'm sorry, f prime of x equals 1 over x. We want to find an antiderivative of this. We should just be able to use the power rule. This is x to the negative 1. So we need to add 1 to the exponent, and the coefficient should be 1 over that number. We got problems. That's not going to work. Adding 1 to that number gives us 0, and we can't divide by 0. So this is the exception to this power rule event. You cannot use the power rule on x to the negative 1 because it will result in weird nonsense that doesn't actually work in any capacity. You can't divide by 0. This is no good. We have to do something else. And in this case, the original function that gives you 1 over x as a derivative is the natural log. Everyone remembers the derivative of the natural log is 1 over x. The antiderivative of 1 over x is the natural log, plus c. That's about all I have to tell you about antiderivatives. I do want to say that just like in derivatives, addition, subtraction, and coefficients are safe. Multiplication, division, and composition are extremely unsafe. And we're going to spend most of Calc 2 coming up with techniques to handle those things. We're not going to worry about them right now. That'll be a Calc 2 event. We're at 17 minutes, so I'm going to see if I can say the last bit really fast. Here's the really unfortunate thing about antiderivatives. They share a symbol with definite integrals. The symbol for an antiderivative is that big curvy S thing. If you put bounds on it, this means a definite integral. Which is the area. Without any bounds on it, if you just do this symbol f of x dx, this is an antiderivative. So like that last example we did, if we're going to do it officially, the antiderivative of 1 over x dx is ln x plus c. That's the notation. That's the end of this video. Hope you liked it.